stoichiometry. This is a prerequisite skill, stoichiometry. Now, most chemistry teachers are going to show you a very traditional approach to stoichiometry, and you may have gotten that in your Chem 130. You may have gotten that in your high school chem. What I'm going to do is on Canvas, I will post Chem 130 videos of the traditional approach to stoichiometry if you feel like you need a review. This is the heart of this course. From this point out, you will have to have a mastery of stoichiometry because we will be using it in everything. And when you get to Chem 152, that's a skill that is supposed to be already under your belt and something that you're going to use and continue to use. So this is a very foundational, basic skill. You've got to make time to learn it because if you don't, you will not do well on that first exam. That first exam that we take on Thursday, that is not an exam on how well you learn the content in this class. That is more of an exam that shows how well prepared you were to take this class. All right, stoichiometry. Let's go over the packet that I have for you here so that we can look at the different pages and talk about what's going to be due when. Now this first page here, this is just a reading, all right? On the type of method I'm going to show you on how to do stoichiometry, which is called BCA. It's not the regular stoichiometry flowchart, like I said, that you've probably been used to in the past, but this is something that we're going to do a little bit different. This is going to summarize the methodology that I use in this class to do stoichiometry and to teach you stoichiometry. So if you don't get it today, this reading will help. Even if you do get it today, this reading is going to help. So make sure it's front and back. And then it goes over some examples here with you. And it goes over each example and it shows you how it works it out, which is what we're going to do in class here. Now, this is the first page. Let's see, this is mole relationships. So this one we're going to make due on Tuesday, 9/10. All right, so that's the first one. That's due Tuesday, 9/10. Front and back of that. This one is also due Tuesday, 9/10, front and back of this one. We'll go over some examples, and I'll actually do some of these problems for you, so you won't have to do the whole packet. All the way up to the end of this page here. All right, so this is the end of this page, page 7, end of what's due on Tuesday, the 10th. So at that point. And if you look down here, you got some answers. And I tend to do that with a lot of these types of worksheets. I'll give you the answers. Of course, you can't just put the answer right in the middle of that space there, right? Because I gave you the answer, you've got to show me the word. The answer I give you so that you can double check your work and make sure that you're doing it right prior to handing the document in to me, right? All right, then we'll go on to the next pages. The rest of the packet, percent yields. That one's going to be due on the day you take the exam, so that's 9/12, so due 9/12. That's the rest of the packet is due 9/12. And once again, the end of the sheets, if you look, a lot of these have the answers there at the end of each of the sheets, particular worksheet that you're on, so that you can make sure that you're doing it. Here's another one, the last one also has the answers for you, so you can do that worksheet and make sure you got the answers. Now on this one, you're probably going to have to put this on a separate piece of paper because there's no way you're going to be able to do the work. This is all just the words. So that's why it says on a separate sheet of paper. Question in the back there. Back row, somebody had their hand up. Yes? Everything else that's not due Tuesday is due Thursday. Whatever. Just get it all done and give it to me by Thursday. Yes?
So I'm going to ask the same thing. You're going to want us to tear it out? Or you just
tear it out. Tear it out. Tear it out and give me what you got. Turn in what you can on Tuesday, and then turn the rest in on Thursday, okay? I'm not going to grade it till the weekend anyways. I just want you guys to get something done before Wednesday night. Right? Because I know how college students are. All right, let's talk about chemistry. Before we can start stoichiometry, we got to do a couple of vocabulary terms. And this is, once again, this is supposed to be review. These are supposed to be prerequisite skills that you come into this class with. And in the traditional approach, one of the things that you have to master and you have to be able to do calculations with is this idea of molar mass. It's also called the formula mass, I've heard in some textbooks. Molar mass, formula mass. Molar mass has to do with the mass of 1 mole of a substance. So there's a whole bunch of vocabulary words before we even talk about definitions here. 1 mole. Now, moles in chemistry are different than moles in biology, right? Moles in biology could be the precancerous skin lesion, right? You should have taken off so you don't get skin cancer. That could be one kind of mole in biology. Another kind of mole in biology is a little furry animal with squinty eyes that digs tunnels underground. All right, that's a biology mole. Chemistry mole is different. What's a mole in chemistry? It's a unit. What does it measure? What does a mole measure? Not mass.
Quantity.
Has to do with quantity. Like bakers have a particular unit that they like to use. When you go to Dunkin' Donuts, what's the quantity that they use? A dozen, right? It's a dozen. So you order a dozen donuts, you know you're going to get 12. Well, in chemistry, 1 mole is this idea of Avogadro's number. If you've ever been to Trader Joe's, they have a type of guacamole dip that's called Avogadro's guacamole. And I always wonder, does it have 6.02 times 10 to the 23rd avocados in it when you make the Trader Joe's avocado dip or Avogadro's guacamole? But it has to do with pieces. A lot of people mix this up with mass, but that is incorrect. It has to do with quantity, and it's an enormous quantity, right? If you took that decimal, you'd have to move it 23 places to the right, so that's a whole lot of zeros. That's a gigantic number. And we use this enormous number because we're talking about itty-bitty tiny pieces of stuff, like atoms and molecules, so we have to use big, giant, enormous numbers. Well, 1 mole mass of anything, you can tell the mass of it based on its molar mass or its atomic mass on the periodic table. So if you look at the periodic table, carbon has a molar mass of 12.01. That means if I wanted exactly 12 atoms of carbon, if I wanted exactly 1 mole, 6.02 times 10 to the 23rd pieces of carbon, would it be reasonable for me to sit out there with a microscope, an electron microscope, and count out atoms of carbon? No, that would not be reasonable. In fact, if you started counting from the number 1, the day you were born, and you never slept, and you counted continuously through your whole life, if you got to 100, you'd never count to a mole. It's such an enormous number. So it's not reasonable for us to count out that quantity. However, the periodic table provides an opportunity for us to figure out how we can get from something we can't see and we can't measure to something we can see and we can measure. And this idea is the equivalency of a mole. So if I wanted exactly 1 mole of carbon atom, 6.02 times 10 to the 23rd, could I weigh out 12.01 grams of carbon? If I had pure carbon, and I gave it to you in the lab, and I said, can you go out and weigh out me 12.01 grams? Could you do that?
Yes.
Absolutely, you could do that. And you would be fairly confident that you'd have pretty close to 1 mole of carbon atoms. That works for compounds too. You can look at the molar mass of a compound, something like lead nitrate, which is really big, or something that's a little smaller, like carbon dioxide. If you look at CO2, the molar mass of carbon dioxide, well, we just said if we had a mole of carbon atoms, 1 mole of carbon is going to weigh how much? 12.01. I like to round to tenths when I'm using molar masses, so you just take what's on the periodic table and round to tenths. So I would say 12.0 would give me 12.0 grams of carbon if I wanted 1 mole of CO2. Well, I'd have to have 2 of the oxygen, right? So I would have to have 2 moles of oxygen, because if I had 1 mole of these pieces, if I had 1 mole of carbon dioxide, I'd have 6.02 times 10 to the 23rd pieces of carbon, right? I'd have a mole of carbon. How many moles of oxygen would I have in 1 mole of carbon dioxide? 2 moles. So 2 moles of oxygen. Each oxygen weighs 16 grams. I'm going to round it to nearest tenth. So 2 times 16 is 32. So if I wanted to weigh out exactly 1 mole of carbon dioxide, I can say it is 44 grams per mole. So this is the idea of molar mass. The units of molar mass, which are generally referenced to covalent or compounds that are non-metal in nature. Formula mass are often in reference to ionic compounds, but it's still the same number. It's still 6.02 times 10 to the 23rd. So if I wanted to know how much carbon dioxide weighs, it weighs 44.0 grams per, now if I'm saying grams per mole, how many moles am I talking about? 1 mole. So I want you to start thinking of these conversion factors not like this, because that's confusing. I want you to start thinking of these conversion factors like this. Now if I want to figure out a mole of lead nitrate, how many leads would I have? 1 lead. How much does 1 lead weigh according to the periodic table? Looks like 207.2, right? 207.2, and that's the PB. How many nitrogens would I have? 2. Each nitrogen weighs 14. 14 times 2 is 28. Is everybody following along here? I'm going through this pretty quick, but like I said, this is a prerequisite skill. How many oxygens would I have in this piece? 6. Each oxygen is 16. 16 times 6 is 96. Based on the oxygen, I add these up. 331.2 grams per mole. So now we all know how to make conversions between molar mass. So if I said I need a mole of this stuff, you could weigh it out by going out and weighing out 331.2 grams per mole. All right, so there's the skill that we need prior to jumping into stoichiometry. You need to be able to convert to moles, and the reason you have to convert to moles is the balanced chemical equations are described in moles. If we look at the reading down here, the very end of page 2, if we look at this equation, H2S plus O2 yields SO2 plus H2O. I can say if I had 2 molecules of hydrogen sulfide, I added them to 3 molecules of oxygen gas, I would produce 2 molecules of SO2 and 2 molecules of water, right? You can also use that in terms of dozens. If I had 2 dozen H2S's, how many pieces of H2S would I have if I had 2 dozen of them? 24, all right? So if I had 2 dozen of those, how many dozen oxygen would I need to completely use up the 2 dozen H2S? Would I not need 3 dozen? Right? Because that's what the coefficients tell you. I want you to think of the balanced chemical equation like a recipe. We've all cooked things from a cookbook before, right? You open up the cookbook and you say, I need 2 cups of flour, an egg, and a stick of butter. All right? Those are quantities. And you go, I got a whole lot of cakes to make. So if I look in the pantry and I see that I've got 10 cups of flour, I got a dozen eggs, and I got a pound of butter, I can make more than 1 cake, can't I? Absolutely, but one of those ingredients is going to run out first, and that's what we call the limiting reagent. The thing that runs out first is the thing that's going to limit how much cakes you can make. In this case, we're making products. So I'd need 2 of those, or 2 dozen of those, 3 of those, or 3 dozen of those. We can also talk about it in terms of moles. If I had 2 moles of H2S, I'd have 2 times 6.02 times 10 to the 23rd pieces of that stuff, right? So if I had 2 moles of that, how many moles of oxygen would I need to completely use up the 2 moles of the H2S that I had? Would I not need 3 moles of oxygen, right? If I had 2 moles of that, I'd need 3 moles of that. What if I had 4 moles of H2S? How many moles of oxygen would I need to burn up all 4 moles of H2S? 6. All right, those are the ratios and proportions that would give you the idea that that's the recipe, right? You open the cookbook up, that's the recipe. You have to know how many pieces you have. If I said you need, for example, you need 3 eggs, but instead I said you have a pound of eggs, that's not going to help a whole lot, is it? What would I have to know in order to figure out how many eggs I have if I have to make that conversion? If I have a pound of eggs and I need 3 for my recipe, what information would I need to know? How many eggs are in a pound, or how much an individual egg weighs, right? That would be information that would be crucial. That's what molar mass is. It tells you how much one thing weighs, and the balanced equation tells you how many of those things you need. So it gets you from a counting quantity that you can't measure to a mass quantity that you can, all right? So this is what we call a BCA diagram. Everybody strap on their chemistry Thinking caps, pull it down tight, take a couple of deep breaths, roll your shoulders back, right? Okay, shake all that sleep off, because this is the hard stuff. Here we go. BCA stands for before, change, and after. If you can use this method to solve stoichiometry problems in this class, when you get to Chem 152, it changes and they call it an ICE diagram, I-C-E. An ICE diagram in 152 stands for initial rather than before. Change is still the same in 152. And you talk in 152 about equilibrium rather than a completion reaction. So if you can learn how to do problems like this in stoichiometry in this class, when you get to 152, you're going to be sending me lots of positive thanks over the arrow bars. And you're going to say, thank you, Dr. Wood, because all my peers in 152 are struggling and they're dropping like flies, and I get it. So I know that it may be tough right now to let go of the stoichiometry flowchart and the traditional way you're learning how to do this, but if you can embrace this, it will help you in lab, and it will help you hugely in Chem 152. All right, so before we can start, what we've got to do with this equation is balance it, right? H2, I think it was balanced on the other side. Wasn't that one we were looking at? Yeah. 2, 3, 2, 2. All right, well, we'll get a little cheating going on there. 2, 3, 2, 2. All right, so now it says in my problem that I've got how many moles of oxygen gas would be needed. All right, so before what I've got, it says I've got 8 moles of hydrogen sulfite to start with. So there's a piece of information that we need from the problem. I've got 8 moles. That's like saying I have 8 eggs. And in my recipe, I need 2 eggs for every time I make a cake. But I've got 8. So I'm going to put 8 moles here. Now, what you need to know is BCA must be filled out always in moles. You cannot use mass, you cannot use volume, you cannot use anything else but moles. So you've got to convert to moles. That's why I gave you that conversion factor right off the bat. You got to know how many moles are there. So I've got 8 moles to start with according to the problem. Now it says how many moles of oxygen gas would be needed. So how many moles of those would be needed? Now to fill out a BCA, you have to think about the chemical reaction. Before the reagents come together, you start out with stuff, but the products have not been created yet. So always in products, at least in this class, that won't be true when you get to 152, but in this class, we're going to assume that our products always start as 0 because we haven't put the reactants together. All right? So now change means everything I'm going to use up. So if I want to use up all 8 moles, I'm going to put minus 8 moles of the hydrogen sulfide, and I want to have none of it left. I want to use every smidgen of hydrogen sulfide that I have available to me. To do that, how many of the oxygen would I need? Well, if you can't figure that out, some of you can probably figure it out in your head, but here's a way to do it when it's not quite so simple as these nice whole numbers. You say, all right, I got 8 moles of the H2S. You can use the balanced equation to go from moles of H2S to moles of the other thing that you need, in this case the O2, because the balanced equation, the coefficients, this is what's called the mole-bridge ratio. The coefficients go right there when you go moles to moles. So H2S, the coefficient is 2. O2, the coefficient is 3. So you need 1.5 times as much H2S as you do, or excuse me, you need 1.5 times as much oxygen as you do H2S. So on your calculator you could do this, or you can simply say, what's 1.5 times 8? 12. So I would need 12 moles of oxygen. So then I would say, I would need 12 moles. I would use up all 12 moles of that, and I would have no oxygen left. But now we need to fill out the rest of the BCA, because that tells us information that's crucial to the last parts of the problems, and you may need that. All right, if I'm starting out with none there, now I'm going to cover this up. We're going to think about it just like the balanced equation. If I have 2 of those and 3 of those, how many SO2s can I make if I have 2 of those and 3 of those? 2. If I have 2 of those and 3 of those, how many H2Os am I going to make? 2. If I have 4 of those and 6 of those, how many of those would I make? 4. All right, you guys get the ratio and proportion. That's the hardest part of stoichiometry right there. That ratio and proportion. All right. So if I looked and I said it's a 2 to 2 ratio here. For every 2 of those I use up, I produce 2 more on the back side, right? So if I'm using up 8 moles of those, it stands to reason how many of those would I make? 8 plus 8 moles. So at the end, I would have 8 moles after. Once again, another 2 to 2 relationship. If I use up 2 and I get 2 out the back end, if I use up 8 here, how many more am I going to get out the back end? 8. So I would create 8 moles here, 8 moles at the end. All right, I used a super simple example at the beginning because I want you to understand how to fill the BCA chart out. It's going to get more difficult. However, before we go to the part that's more difficult, are there any questions where these numbers came from right now? You've got to totally be present in the next 45 minutes to listen to everything. Do not allow yourself to daydream. Luckily, I'm recording all this stuff. Yes?
Where did the initial rules come from?
Good question. In the problem. So you're going to look and there's going to be something in the problem that tells you the information that you need to start with. Remember, this is the recipe. What they're saying is you're starting with 8 moles. So you're going to put that as the before.
I
So
meant the equation, like the 2, 3, 2.
that was just the balanced,
Oh, okay.
the coefficients you needed to balance the equation. That's why we do balancing equations before we start stoichiometry. Yeah, back
On
row.
the change, where do you get the +8 and +8? I'm still kind of confused on the whole ratio deal that you were doing.
Okay, well, if we look at the original problem, it's like baking a cake, right? I need 2 eggs and 3 cups of flour to make 2 cakes, all right? If I had 4 eggs and 6 cups of flour, how many cakes could I make? Twice as many, right? All right, that's where the ratios and proportions are coming from. If you're starting with 8 and you need 2 to make 1 recipe, you're going to be able to make more than 1 recipe, right? So you're going to be able to go through this reaction more. So if you use up all 8 of those, right? All 8 of those, what I did was I related the moles of H2 to the moles of H2S, crossed it out, figured out how many moles of O2 I used, or I would need, to burn up all 8 of those. You could do that in your brain with a simple ratio and proportion, all right? All right, let's go on to the next one. Propane, which is C3H8. Whoopsie, H8. Now, if it's propane, what do you think it's going to be, solid, liquid, or gas? You can come sit up here, honey. Gas, right? All right. Burns in air. Well, if it burns in air, what does it need to burn in air? Oxygen gas. O2, remember, is oxygen gas. Yields carbon dioxide and water. What's the formula for carbon dioxide? CO2. That's going to be a gas because it's going to be pretty darn hot when you're burning stuff. And H2O is good old dihydrogen monoxide. And you could put liquid, but since it's in a combustion reaction, I'd say it's probably going to be a gas because it's pretty darn hot. Now we got to balance this. So you guys balance it and tell me what the coefficients are. Somebody have the coefficients yet? What are they?
We have just one C3H8 plus 5O2 turns into 3CO2 and 4H2O.
That looks pretty good. Let's double check. 3 carbons, 8 hydrogen, 4 times. Yep, looks good. All right, so the problem tells us if 12 moles of carbon dioxide are formed. So there's the key. So you got to read this and think about what it is it's telling you. That's not information you're starting with. That's not what you began the chemical reaction with. That's what was created at the end. So that's why I'm putting 12 moles there. It says if 12 moles of carbon dioxide are formed. We're going to say that we started out with none, right? Because we got the before, change, and after. So the products would have none, and we formed 12 moles. So we're going to say water had none also. Now let's look and think about what's going to happen. Well, if we made 12 moles of carbon dioxide, it's a 3 to what ratio? Would it be easier to compare 3 to 5 or 3 to 1? I think 3 to 1 would be easier to compare. Well, if I made 12 of those, would I use less than 12 or more than 12 of the original propane? Less. But like 1/3 less, right? Because for every one of these I use up, how many of these do I make? 3. So I use 1/3. If you're not sure how to do that, you can do it using math. You say you got 12 moles of the CO2 to start with, and you want to go from moles of CO2 to moles of the C3H8, right? Coefficients. What's the coefficient in front of C3H8? 1. What's the coefficient in front of CO2? 3. So what's 1/3 of 12? 4. All right, they won't all get this easy. All right, so I'm going to put, I must have started with 4 moles of this stuff, right? I used up all 4 moles of it, and I had none left over. Well, now I've got some things that I can compare because a 1:5 and a 1:4 ratio are way easier, right? All right, if I started with 4 moles of those and I used it all up, how many moles of oxygen must I have started with? 20. Excellent. Does everybody see where that number comes from? Some people get this right away and other people it takes a while. So we're going to use up all 20 moles of that. We're going to have none left over. All right, what would be easiest to compare and figure out how much water I made?
1 to 4.
I like 1:4, right? 1:4 is pretty easy. If I used up 4 of those, how many waters would I have produced? 16 plus 16 moles. All right, so I got 12 moles of that at the end. I got 16 moles of that at the end. Now, if I said, for example, in the problem, what's the mass of water that would be produced? Could I determine the mass of water produced based on the information in this problem?
Yes.
I certainly could. I could start with 16 moles of water, right? And that's what a BCA is beautiful for because it's got all that information and all you got to take it at the end is what's left and change it back into the units that you need. If I want to go from moles of water, what would I need to do to figure out how many grams of water I need?
1 mole.
To grams of water. So you can go moles to grams. Moles to anything else, one's in front of moles. How much does a mole of water weigh in grams? 18 grams per mole, right? There's 1 oxygen, which is 16. 2 hydrogens, 1 each, that's 18. So you could figure out the mass of water that was produced. All right. Let's go to a little bit more complex one. Turn over on the other side. See, I'm doing all this homework for you, huh? You know what you're doing. Here's a good one. We'll try number 4. Poison gas is always a fun one to do reactions for. Here we go. Poison gas, COCl2. It's a gas. Reacts with water in the lungs. So how would I symbolize that? Plus H2O. What form would the H2O in your lungs be in, most likely?
Gas.
Gas or liquid. We'll say liquid, that it was in the tissues of your lungs. To form hydrochloric acid. What's the formula for hydrochloric acid? You don't want to breathe that stuff if it makes hydrochloric acid out of water in your lungs. Owie. That's not good. Plus carbon dioxide, which is CO2. That's going to be a gas. All right. Let's see. Balance that one. Tell me what the coefficients are. Is it balanced already? No, I don't think so. Is it? Maybe it is. No, we need 2. I think we need that for sure. Is that it?
Yeah, I think that's it.
I think you might be right. All right, we'll go with that. All right, how many moles of hydrochloric acid would be formed? All right, so we want to know how many moles of this stuff would be formed by 0.835 moles of phosgene. So if we started out, I messed up and I got the equation. So we'll make this we'll put the B right here, right underneath the equation, and then change an after. All right, 0.835. So 0.835 moles of this stuff is what we're starting out with. And we want to use it all up. So I have none left. Well, if I had 0.835 moles of this stuff and it's a 1-to-1 with water, how much water should I have started with? 0.835. That was easy. Got 0 left over. All right, now it gets a little more complex. If we assume that we're starting with 0 of those 2, 1 to 2 ratio is pretty good. What would I do to 0.835?
Multiply by 2.
What's 0.835 times 2? 1.67, thank you. And what would I compare CO2 to?
1 to 1.
Anything 1 to 1. So both of these are 1 to 1. If they used up 0.835, how much CO2 would be made? 0.835. See, these are kind of fun. And they're super helpful when you get to lab and you've got to make some predictions. Oops, wrong one. 1.67 moles of that stuff. All right. Now we're going to add the microscopic perspective to our BCA ideas. You will have to do this operation on the first exam you take a week from today. There will be a subjective portion on the exam that will look just like this. It won't be the exact same problem. It'll be a different problem. But you will have to draw the pictures that I'm going to draw for you now in a similar way with a new equation. So if you don't get this, make sure you practice on this homework problem. All right, write the balanced equation for the reaction between hydrogen and oxygen. All right, well, hydrogen in its natural form, its elemental form, as a gas is going to be what formula? H2 as a gas, plus oxygen in its elemental form as a gas would be O2. And guess what we make when we put these things together? Good old H2O. This is the reaction that we should be focusing on now instead of our fossil fuel burning vehicles. If we could, this reaction is totally reversible. You can take water and split it up into oxygen and hydrogen gas using electricity. The electricity could come from solar panels, which is very efficient. You can make a solar panel and they'll last for 50 years. You hook it up to a container of water, it'll make lots of oxygen and hydrogen gas. The oxygen can be used for all sorts of industrial purposes. Hydrogen is the cleanest burning fuel we have. If the Detroit auto manufacturers, instead of building Hummers 20 years ago, had focused on hydrogen as a fuel, and we had created a hydrogen economy in the United States, and instead of having gas stations everywhere, we had hydrogen filling stations, we would have a handle on global warming, the economy would be better, we'd all be driving around completely clean fuel, and when you take hydrogen and you combust it in an internal combustion engine with oxygen, all that you get out the tailpipe is a drip of water. No unburned hydrocarbons, no particulates, no greenhouse gases, none of that stuff. Hydrogen is the fuel of the future. So y'all have to fix what my generation screwed up. Figure out how to make some hydrogen cars and build a hydrogen economy. They've got the technology. The problem is we need a hydrogen economy. Yes?
What happens to the extra oxygen?
Well, let's balance it. We got H2 and H2, O2. I think we need a 2 there, and then I think you need a 2 there. So there's where it goes. You just need 2 hydrogens every time you make that. All right, so if we got, let's start with our BCA here. I'm going to bring the balanced equation down here. 2 H2s plus O2 yields 2 H2Os. All right? Now they're telling us we've got 4 molecules of hydrogen gas and 4 molecules of oxygen gas. We can also say that's 4 moles. You could even say it's 4 dozen. So you can think about them as individual particles, you can think about them in terms of dozens, or you can think about them in terms of moles. That coefficient can count for any one of those quantities. Right now we're just going to think about them as molecules, but it also works for moles. I'm going to make a little legend here. This is going to be my H2, and I'm going to make it smaller because hydrogen is a very small diatomic molecule. And I'm going to make O2 bigger, and I'm going to make the circles open so we know which one is H2 and which one is O2. And that problem tells me I've got 4 molecules of hydrogen and 4 molecules of oxygen. That's the same as if you had 4 moles. So I'm going to say I had 4 moles of hydrogen and 4 moles of oxygen to start with, and I had 0 of the water initially. Now I want to draw what that looks like in the box, so you have to think about, now your molecular geometry doesn't have to be perfect, but I want to see molecules that represent what they are supposed to be. If it says H2, it should be a molecule that is connected together. It should not be 2 independent H's. It should be not be a single H by itself. So we're going to write 1. There's 1 molecule of H2. 2, 3, 4. You can put them randomly in your boxes wherever you want. because we're starting with 4 molecules of hydrogen gas. We're also going to start with 4 of the oxygen. So somewhere in your box, put 4 oxygen molecules. And we're going to pretend they're gases, so they're randomly bouncing around without any apparent motivation inside our box. All right. So that's the container before. Now, what I'm going to do is I'm going to transfer from the before. This is before the reaction. This is after the reaction. And I'm going to make some molecules of water. So over here on my product side, I'm going to show water molecules existing by 1 oxygen and 2 hydrogens. This is going to be my H2O. So now I'm going to take molecules out of the first box. I need 1 O, so I'm going to cross it out, and 2 H's to make my first molecule of water. So you randomly choose 1/2 of one of your oxygen molecules, cross it out, and 2 pieces of hydrogen. All right, make another one. I'm going to cross out the other one of those. I'm going to cross out 2 more hydrogens. I'm going to transfer over here. This is the microscopic as well as the symbolic that we're going through now. Same thing, I'm going to use another one of those. I got to use 2 more hydrogens up. I'm going to make another molecule of water. Make another one. All right. Well, it looks like I can't make any more water. How come? We ran out of hydrogen. So I still have to put what's left over in here because they didn't just disappear, right? They're still in my box. That is what we call the, nope, that's the excess. That's the excess reagent. That's the stuff we had left over. And the hydrogen was the limiting reagent. Stuff that went out and got used up first, all right? So now the question says, how many molecules of water can be produced? Well, how many did you make? 4, right? Which reactant is in excess? O2. Why? Because it was leftover, right? Didn't get used up. How many molecules of excess reagent are there? Not atoms. How many molecules? 2, because we're talking about molecules, moles, or dozens. All right? So let's look at that and depict this in our BCA. Looking at just the balanced equation. If I had equal amounts of both things, which would get used up first, the hydrogen or the oxygen? Hydrogen would get used up first because for every 2 of those, I only use up 1 oxygen, right? So if I got 4 of those, I would have used up all 4 moles. I would have 0 left over. If I use up 4 molecules, or all 4 molecules of my H2, and I only need half as many of the O2, how many of those would I use up? 2. So minus 2 molecules. That means I'm going to have 2 left over. Now, if I compare, what would be easier to compare? 1 to 2 or 2 to 2? But now we have to remember what got used up. So you have to remember. So we have to base it on our limiting reagent, in this case, which is 4. So if I used up all 4 of those, and it's a 2 to 2 relationship, how many of those would I make? 4. So plus 4 moles, and at the end, I would have 4 moles of it left over. Okay. I'm going to go on. This is one I would recommend that you practice. I'm going to let you do that one on your own. Let's do some BCA with these problems that we've got now. All right, let's try number 4 here. When sodium hydroxide reacts with sulfuric acid. All right, what's this formula for sodium hydroxide? Sodium hydroxide is NaOH, okay. And this looks like an acid-base reaction, so what form do you think it would be in? Solid, liquid, gas, or aqueous solution? Most likely an aqueous solution, because we've got to have the ions in there. Plus sulfuric acid, they gave us that nice formula for. So anytime it's an acid, it's going to be an aqueous solution. Now this is a neutralization reaction, which we haven't talked specifically about in this class, but I would encourage you to watch the videos on types of reactions that I'm going to post, which will give that to you. Since this is an acid-base reaction, what are the two things that are always formed in an acid-base reaction? Water is one of the things that's always formed, and it's a pure substance, plus what else? A salt of some kind. And the salt is usually whatever's left over. Remember, salt is an ionic compound. It's a metal-non-metal combination. So if we took the water out of here, what would be left over? The Na and the SO4. Now we've got to make new nomenclature. It's not the way that it goes together necessarily. Sodium, based on the periodic table position, has a +1 charge. What sulfate has a polyatomic ion? -2. All right, what's the formula for sodium sulfate? Na2. I'm going to encourage you to make sure you double check your formulas for your products. The nomenclature must be correct. If you cannot balance an equation you've written, it's probably because the nomenclature you wrote is incorrect. I'm going to say it again because it's important. If you find you're having a hard time balancing an equation, go back and check the nomenclature of the products. That's usually where the error lies. You got to fix the nomenclature of the products, then go back, and usually it's much easier to balance it. All right, let's balance this thing. Looks like we probably need a 2 there, right, to fix the sodiums. Got a sulfate and a sulfate. We got, let's see, 2 oxygens. 4 more is 6. We got 4 there. I think we probably need a 2 there, right? That gives me 6 oxygens. Hydrogens, we got 2 and 2 is 4. Okay, I think we're good. I think we're balanced, all right? Okay, so we're going to do a B, C, A. I like to draw a line in between the B and the C and the A. It says, calculate the mass of sodium sulfate produced. All right, there's the sodium sulfate. We're going to say it's an aqueous solution because there's the driving force of our reaction. Calculate the mass of sodium sulfate produced. So we want to know how many grams of this stuff. And in this BCA, I always draw pictures. That's what physics taught me, is draw pictures of everything. Science people, we are good at taking this information and changing it in our minds, but if you can change it into a picture on a piece of paper, it's going to make it much clearer for you to try and work these problems out. All right, so if we've got the mass of sodium produced when 15.5 grams of sodium hydroxide. So we got, of this stuff, we got 15.5 grams of it to start with. And we got 46.7 grams of this stuff. So 46.7 grams of that stuff. Well, I told you at the beginning of this BCA experience that what is the type of units we have to use in BCA to calculate? Moles. So what do I have to do with these masses? I got to turn them into moles. So we're going to do that first. So I say 15.5 grams of the NaOH. And I got to figure out the molar mass to go from grams of NaOH to what? Moles of NaOH. This is your molar mass conversion. Moles to anything else. 1 always goes in front of moles. To figure out a molar mass of sodium, let's see, sodium is 23. I'm rounding it to tenths. Oxygen is 16. Hydrogen is 1. 40 grams per mole. All right, somebody with a calculator, what's 15.5 divided by 40?
0.387.
0.387. And what are my units here? Moles of NaOH. All right, so there's my first bit of information I'm going to put under the B and for BCA. So I have 0.387 moles of this stuff to start with. All right, got to do the same thing with the H2SO4. All right, 46.7 grams of the H2SO4. I'm going to go from grams of H2SO4 to moles of H2SO4. Got to calculate the molar mass. Let's see, hydrogen is 1 each. That's 2. Sulfur is 32.1. Oxygen is 16 each times 4. 64. 98.1 grams per mole. Hopefully I got that right. All right, what's 46.7 divided by 98.1? 0.48. Is there one more digit there?
Yeah, 0.476.
All right, 0.476 moles. I want to go with sig figs here, right? Because we started with 3 sig figs, we want to carry 3 sig figs through. So we got 0.476 moles of this stuff. Told you they were going to get harder, right? I don't want to disappoint you. All right, well, let's see. It's hard to tell what you're going to use up first in this case, right? Which one gets used up at a faster pace, just in general? The sodium hydroxide or the acid? Which one gets used up faster in the equation? Sodium hydroxide. Does it look like we got twice as much? Probably not, but so I would think that probably all that gets used up. But we can double check fairly easily, right? We can double check and see. Well, if we got 0.387 moles of the NaOH, and I want to know moles of NaOH, compare that to moles of the H2SO4, how much is going to get used up, that I know that it's a 1-to-2 ratio, right? So what's 0.387 divided by 2? 0.166. 166. 0.387 divided by 2?
0.19 something. Yeah.
Okay. Oh, that's right. I didn't do it right. 0.194. All right. Moles. All right. So it looks like the NaOH is the limiting reagent, right? Because if I used up all that I have, how much of this would I use up? On 0.194. Do I have more than 0.194? Yes, I do. Everybody see how I got those numbers? All right. So I'm going to use up all 0.387 moles of this. How much am I going to have left? 0. All right. How much of the 0.476 would I use up? 0.194 minus 0.194. Somebody with a calculator. What's 0.476 minus 0.194? Thank you. 0.282 moles left. I'm going to assume I'm starting with 0 of those. All right, now we can start looking at some ratios and proportions here. You got to look at the change when you want to compare back and forth. Don't look at the beginning, right? You want to look at what changed to compare the ratios. So what would I compare water to? What would be easiest to compare? The sodium hydroxide. If I used up 0.387 of that, how much of this would I make? 0.387 plus 0.387 moles. So I would have in the end 0.387 moles of this. All right. Once again, I'm going to use the change column to compare, not the before or the after. What should I compare my sodium sulfate to in my equation? The sulfuric. All right. If I used up 0.194 of the sulfuric, how much of the sodium sulfate would I have created? 0.194. I know it seems pretty easy here to some of you, but when you get to doing this on your own, maybe not so much. All right, so now that's not grams, that's 0.194 moles of the stuff. But the question asked me, they need to know the mass. So what should I do with that? Convert 0.194 moles of Na2SO4, and I want to go moles of Na2SO4 to grams. Let's see, sodium is 23 each, and there's 2 of them, so that's 46. Sulfur is 32.1. Oxygen is 16 each, so that's 64. $142.1 it looks like per mole. All right, what's 0.194 times 142.1 if I did my math right? No, it's much bigger than 0.001. How much?
27.
27?
Yeah, 0.5674.
674. Okay, let's go some sig figs here. What are my sig figs going to tell me? I would say 27.6 I would use, and that's going to be grams of Na2SO4. Let's double check and make sure that's the right answer. What question was that, number 4? Well, they rounded it a little bit different, but that's okay. See, that gives you a little confidence there that you're doing the problems right. All right? Okay, onwards, onwards. Percent yield, hot diggity dog. Now this is going to be something that you are going to use a lot in lab. And there's two types of comparison in lab. There's percent yield and percent error. And let's talk about each of those. So percent yield versus, and this always used to drive me crazy because students use both interchangeably and they're very different ideas, percent yield, percent error. All right, percent yield versus percent error. Percent yield is how much you did make compared to what should have been made. All right, so what do I mean? So percent yield, here's the formula. Percent yield is equal to the theoretical yield, oh, excuse me, wrong one, actual yield divided by theoretical yield times 100. All right, where do these numbers come from? Theoretical yield is using stoichiometry. Meaning, in a perfect world, we look at these chemical equations and we say, all right, we've got 2 of these and 3 of these, they're going to react, we're going to put them over the product side. We've got 2 more of these, 3 more of these, react and put them over the product side. In a perfect world, does that always happen? Do you use up every single thing that's possible? No, it's impossible, because what happens in a chemical reaction, and you talk a lot more about this when you get to Chem 152, it's a topic called kinetics and reaction mechanisms. And what that means is when reactant particles come together, the first thing they need is sufficient energy. They have to hit each other with enough energy to break the bonds that already exist in the molecules and reform new ones. That's the first criteria that they have to have. The second criteria, when they hit each other in order to react, they have to hit each other with sufficient energy, but they have to hit each other in the right orientation. Right? So what that means is that not every single thing reacts that it should. And so what we often get is less than we count on. And actual yield comes from your experiment. So that's actually your experimental value, how much you actually created in the experiment. So stoichiometry tells you how much you should have made. You actually measure the product in your reaction, the mass of the stuff you made, and that tells you your actual yield. Now, that idea is a different way to compare. This is an idea used to compare chemical reactions. Right? All right. Other times in lab, you're going to be comparing and you're coming up with some number that you compare to a standard. For example, specific heat of a metal. Each metal has its own heat capacity, and in one of the labs that you do in this class, you measure the heat capacity of a metal. So I know that aluminum's heat capacity is, I think it's 0.270 joules per grams degrees Celsius. Now, what kind of strange information is that for a person to remember in their brain? But what you would do is you'd say, okay, that's the standard. That's what it's supposed to be. When I did my experiment, here's what I figured it to be. And so your percent error is a different kind of calculation. You will still use it in lab, but it's used in a different situation where you have a standard that you're comparing against rather than a chemical reaction that you perform. So percent error is the absolute value of the difference between the theoretical value and your experimental value. So the absolute value of the difference, so it's not positive or negative. Percent error is never a plus or minus number. It's just a percent, flat out, all right? Divided by the theoretical value times 100. All right, we're not going to use this one a whole lot in this class, but you will use this one a ton in lab. We tend to use this one more in stoichiometry because we're comparing chemical reactions, what you should create compared to what you did create. All right, with that idea in mind, let's do some problems with percent yields. Okay. let's try number 3. Look at number 3. All right, number 3 says, suppose 4.61 grams of zinc. All right, so we got zinc, which is, since it's a metal, it's going to be in solid state, was allowed to react with hydrochloric acid, good old HCl, aqueous solution, to produce zinc chloride. Uh-oh, now you got to use your nomenclature skills. What's the symbol for zinc chloride? Zn and Cl, but now what's the subscripts that go along with that? I see some heads turning to the periodic table, which makes me happy because they're looking for charges.
It's two. The N is 2.
So then that would be ZnCl2, right? All right. Let's see. Is this one going to be soluble or not? The halogens are generally soluble, except if silver, mercury, and lead shows up to the party, and that's not silver, mercury, or lead. So I'm going to say that's probably soluble. And what else? And hydrogen gas. All right, H2 gas. Let's see. I don't think that's balanced, but I think if we put a 2 there, that probably fixes everything, doesn't it? Yeah. All right. So if we got 4.61 grams of this junk, 4.61 grams of that, allowed to react with hydrochloric acid, so we must have excess of this stuff. So we must have a lot of that. How much zinc chloride should you get? So we want to know what's the mass of the zinc chloride that I'm going to start with. Well, more practice with BCA. All right, what do I got to do with that zinc before I can start my BCA? Convert it to mole. So I got 4.61 grams of zinc, and I'm going to go from grams of zinc to moles of zinc. Zinc on the periodic table, where's zinc? Looks like 65.4. All right, what's 4.61 divided by 65.4?
0.070.
All right, moles of zinc. So if we got 0.070 moles of the stuff, we don't know how much hydrochloric. Well, we're going to have lots of it because they didn't say that we had limiting. All right, they want to know how many grams of the zinc chloride. Well, I'm assuming I'm going to use up all that stuff because I got plenty of hydrochloric, right? I got lots. So if they don't, bless you, if they don't tell you how much you got, you can assume you have more than enough to react every single bit of what you got. If I use up all of this, how much of the hydrochloric will I use up? 0.14, right? Wouldn't I use up 0.14 moles of it? Remember, you got to compare the change column when you want to look at the ratios and proportions between the two. You don't want to look at the before or the after. You want to look at the change column. All right, now zinc chloride, what would be easiest for me to compare it to, the zinc or the HCl? Probably to the zinc. So if I used up 0.070 of that, how much of that would I create? If I started out with 0, I would create 0.070 moles. If I start out with 0 of the H2, how many moles of H2 would I make? Same thing, right? So in the end, I'd have 0.070 moles of this, 0.070 moles of that. I would have 0 of that, and I would still have lots of that left over. But they wanted grams, so what should I do? Convert the 0.070 moles to grams. All right, so we're going to go from moles of zinc chloride to grams of zinc chloride. See, zinc weighs 65.4. Chlorine is, I think, 35.5 each, so that's 70 for chlorine. There's 135.4 grams per mole. All right, somebody with a calculator, what's 0.070 times 135.4? Grams of zinc chloride. All right, let's see if our answer is right. Hold your breath. What number was that? Number 3? 9.61. Well, we probably rounded our molar masses a little bit different. But that's not the end of the problem. Oh, I forgot. There's more in the problem. Okay, so this is, what is this? This number, what does that mean?
That's how much we should get.
That's how much you should have made if it's a perfect world. If every single piece that you had available was able to react, okay? But it's not a perfect world. And in fact, never do you get 100% yield in chemistry, and chemists spend their lives and their careers trying to increase the percent yield in a particular chemical reaction because it just makes it more economical, right? That's what chemists do a lot of. They try to increase the percent yield. So here's how much we actually did make. So if I want to calculate the percent yield on this particular chemical reaction, what would I do? So I would take my 8.56, which is what I actually made of the zinc chloride. I divide it by how much I was supposed to make of the zinc chloride times 100, right? And that should get me, what number is it supposed to be?
90.
About 90%, right? About 90%. All right, let's look at the traditional way of stoichiometry real quickly, just as a review, so that you can see that. I'm going to put the videos and post those up. If you could also do this problem using the traditional approach, right? Okay, the traditional approach to stoichiometry says you take grams or number of particles, and you convert them to what first? Moles of that first thing. Then you can go from moles of the first thing to moles of the second thing, and then you can go back to grams or to number of pieces. This is the mole bridge ratio. So if we were going to use the traditional stoichiometric approach, you could, because this is not a limiting reagent problem. It's not a limiting reagent problem because we have lots and lots of that stuff, and we know that every smidgen of that zinc is going to get used up, so I can use the traditional stoichiometric approach. In this case, I'm starting with grams and I want to get to grams. So I'm starting with grams, I want to get to grams. It would cost me 1, 2, 3 conversions. So I start with the 4.61 grams of the zinc. I'm going to have 1, 2, 3 conversions to get me from grams of zinc to grams of zinc chloride. So I'm going to go from grams to moles first. So I'm going to go grams of zinc to moles of zinc. That's my first step. Then I'm going to take moles of zinc. I'm going to put it down here because I want those units to cancel. I'm going to go from moles of zinc to moles of zinc chloride. Moles of zinc chloride. I'm going to take moles of zinc chloride. I'm going to put them down here because I want them to cancel. And I want to go from moles of zinc chloride to grams of zinc chloride. So there's the traditional method. And then you go back and you fill in the numbers. Moles to anything else, 1 is in front of moles. Moles to something else, 1 is in front of moles. When you got 2 moles, where do you get the ratios and proportion for that conversion? From the balanced equation. So we look at ZnCl2 is a 1. Zinc is a 1, so it's a 1-to-1 ratio. I would just put the molar mass there, the molar mass there, and I could do the stoichiometric traditional way. I will post a complete lesson on this approach. This is traditional stoichiometry. You can use either approach to solve the problems. Here's my advice. First of all, if all this seems very foreign to you and you're having a hard time following along, you got a lot of work to do this weekend. I would clear my schedule. I would view the first 2 videos of Chem 130 first, look at the traditional approach, make sure I understand that flat out, and then I would view the video that we just went over again. You will have to use both methods, and using both methods is going to make you a better chemist. It's going to make you think about chemistry and understand it deeper. Here's a strategy when you're taking exams or tests that involves stoichiometry. Works for this class, for 151. Any of the high stakes tests you have, GRE, MCAT, PCAT, they're all going to ask you stoichiometry problems. I can guarantee it. I've seen all those exams before. In fact, I've graded those exams, and they always have stoichiometry problems. You got to look at the problem and figure out the most efficient approach to solving the problem. If it's not a limiting reagent problem, often the most efficient approach is simply flat out traditional stoichiometry if you don't have to deal with limiting reagents. However, if it's a limiting reagent problem, it is often best to use BCA because you've got all the information there. It keeps it in a nice accounting. BCA is like accounting for chemists. If any of you have ever taken an accounting class, they have, you know, the expenses and the payback, and you subtract things, and you come at the bottom to the final sheet of money that you have after everything is resolved. That's kind of like what BCA is. BCA is like an accountant's version of keeping track of stoichiometry. So, if this all seemed very foreign, like I said, clear your schedule, call in sick to work, make sure that you understand this because this is hard stuff, and the rest of the course will depend on you understanding stoichiometry. And the first, bless you, the first exam in this class will be very stoichiometry heavy. So make sure you know how to do this, and if you have questions, make sure you go to the tutoring center as well. All right. That's it for today.